Welcome back to the Deep Dive. We're continuing our journey through the online encyclopedia of integer sequences, aimed especially at number theory students.
That's right.
Today, we're getting into OEIS sequence A000209. And our plan, really, is to figure out what this sequence is all about, why it's interesting if you're into number theory, and maybe get a better handle on the tangent function itself. It can be a bit tricky.
It certainly can.
We're pulling from a few places today. Advanced Trigonometry, a really good Reddit thread, actually, about understanding trig functions using the unit circle.
Oh, that's a useful perspective.
The OEIS entry for A000209, naturally, and Wikipedia's article on trig functions. So quite a bit to work with.
Sounds good. So this sequence, A00000099, its definition sounds incredibly simple on the surface.
Right.
It's just the nearest integer to tan. That's it.
Nearest integer to tan seems straightforward.
But, well, as you often find in mathematics, that simplicity hides some, let's say, interesting behavior.
I bet. Okay, so before we jump into the sequence itself, maybe we should quickly refresh our memory on the tangent function. What are the key ways to think about it?
Good idea. The most common starting point, probably from school, is the right-angled triangle.
Yep.
Tan of an angle is the length of the side opposite the angle divided by the length of the side adjacent to it.
Opposite over adjacent. Got it. That's the classic definition. But you mentioned the unit circle perspective from that Reddit discussion. How does that help?
Well, the unit circle gives you a much bigger picture, really. Imagine that circle, radius 1, at the origin.
Okay.
Draw a line from the origin out at an angle, let's call it theta, from the positive x-axis. Keep extending that line until it hits the vertical line by 1. The tangent of theta is just the coordinate of that intersection point.
Ah, I see. So it's literally where the radius line extended cuts that tangent line at x1. That visual feels, I don't know, more continuous somehow.
Exactly. It lets you define tangents for any angle, not just the acute ones in a triangle. And it helps visualize some key properties.
Like its periodicity.
Precisely. Tangent repeats every pi radians. You can see that on the unicircle rotate by pi, and the line points exactly opposite, but its extension hits that x1 line at the same height, just mirrored initially. Then another pi brings it back.
So a period of pi, unlike sine and cosine, which are 2 pi.
Correct.
And what about those points where tangent just goes haywire, where it's undefined?
Ah, yes, the asymptotes. Those happen at pi over 2, and any integer multiple of pi added to that. So pi over 2, 3 pi over 2, minus pi over 2, and so on.
Why there?
Think about the unit circle again. At those angles, the line from the origin is pointing straight up or straight down.
Vertical.
Right, it becomes parallel to that line x sees 1.
Yeah.
Parallel lines.
Never meet. So no intersection point, no defined tangent. Makes sense. And the triangle definition.
Same reason, essentially. As the angle gets close to 90 degrees, the adjacent side shrinks towards 0. Opposite over adjacent means you're dividing by something vanishingly small.
Division by 0 territory. Got it. Wikipedia also mentioned a series expansion. Is that useful here?
It's important in analysis. For angles x with absolute value less than pi 2, tan x is x plus 13x cubed plus 215x fifth power, and so on.
An infinite sum.
Yes. Very powerful for theory, for approximations, but maybe not the most intuitive way to grasp this particular sequence, A000209. At first glance.
Okay. Good to know it exists, though.
Okay.
One last thing. On tangent itself, the connection to slope?
Oh, absolutely fundamental. The tangent of the angle a line makes with the positive x-axis is the slope of that line. Rise over run, opposite over adjacent. It's the same ratio.
Right. Connects trigonometry right back to basic coordinate geometry. Okay. So solid foundation on tangent. Let's look at the sequence again. A000209, nearest integer to tan n. What did the first few terms look like?
Okay, let's see. It starts 02, negative 2, 0, 0, 1, negative 3, 0, 1, negative 7, 1, and then quite dramatically, negative 226.
Whoa! 0, 2, negative 2, 0, 1, then minus 226. That's quite a jump. It definitely doesn't look like, say, an arithmetic progression.
Not at all. It seems quite erratic. Jumpy, you have these small integers, zeros popping up, and then suddenly this large negative value.
And the OEIS entry had that comment about Richard Feynman, right? About tan hen 100.
Yes. A great little anecdote. Apparently, he couldn't quickly estimate tan 10 to the power of 100. It just highlights how incredibly complex the behavior of tan x can be for large arguments.
Even for seemingly simple integer arguments like, well, 10 to the 100 is huge, but the concept is simple.
Exactly. And crucially, we need to remember that n here is in radians.
Yeah.
That's the standard in analysis unless you specify degrees. So tan, it means tangent of n radians.
Right. Not n degrees. That would be a very different sequence. So, okay, why does nearest integer to tan n produce such a wild-looking sequence? What's the math behind the apparent chaos?
The core issue, fundamentally, is the irrationality of pi.
Ah, pi always showing up.
Always. Tangent has its zeros at integer multiples of pi, 0, pi 2, pi, and its asymptotes, where it blows up at odd multiples of pi 2, 3p2.
Okay.
Now, because pi is irrational and integer n, our argument, is almost certainly never going to be an exact multiple of pi nor an exact odd multiple of pi.
It'll always be just slightly off.
Precisely. Think about the values of n just by themselves. 1 radian, 2 radians, 3 radians. Where do these points fall when you wrap them around the unit circle? Or, more formally, what are the values of n modulo pi?
The remainder when you divide n by pi.
Sort of, yes. Because pi is irrational, these values in mod pi, the fractional parts, effectively end up being densely distributed in the interval from 0 to pi.
Densely distributed, meaning they vitally get close to every possible value in that interval.
That's exactly it. Over time, as n increases, the value n radians will land arbitrarily close to any angle between 0 and pi.
Okay, I think I see where this is going. If the n radians can get arbitrarily close to any angle,
then tan can get arbitrarily close to any real number. It can get very close to 0 when n is near a multiple of pi, or incredibly large positive or negative when n is near an odd multiple of pi 2.
and since tan can approximate any real number, the nearest integer to tan can be, well, any integer, or jump around unpredictably.
That's the essence of it. The sequence jumps because n odd pi wanders all over the place, pushing tan through its entire range of values, from negative infinity to positive infinity, hitting values near integers seemingly at random intervals.
So that negative 226 for n at 12, that just means tan 12 radians happens to be really close to negative 226.5.
Exactly. It means 12 radians must be just slightly more than an angle like 3 pi 2 or 7 pi 2, where the tangent is heading towards negative infinity.
Fascinating. It's like the discreteness of the integers interacting with the continuous irrational nature of the tangent function. Looking at those first few terms again, 0, 2, 92, 0, 1, negative 3, 0, 1, negative 7. Do we see any hints of structure, even if it's temporary?
Well, the zeros are easy. They happen when n is close to a multiple of pi, so tan n is close to 0.
Like tan 3 is close to tan pi, which is 0.
Yeah.
The nearest integer is 0.
Right. And tan 1 is about 1.557, nearest integer is 2. Tan 2 is about negative 2.185, nearest integer negative 2. The small values occur when n isn't particularly close to either a 0 or an asymptote. The value 1 appears when n is near pi 4 plus k pi, roughly.
But that big jump to negative 226 tells us that any local pattern is, well, probably just a coincidence.
Very likely, yes. The underlying driver is this dense distribution modulo pi. Predicting the next term requires knowing tan plus 1 with high precision, which depends sensitively on how n plus 1 radians relates to the multiples of pi and pi 2. It's not a simple calculation in the long run.
It really makes you appreciate how complex seemingly simple functions can be. Does this complexity mean tangent is mostly a theoretical curiosity, or does it actually show up in the real world?
Oh, it definitely shows up. Despite its sometimes wild behavior, its core definition as a ratio is incredibly useful.
Like where?
Architecture and construction rely on it heavily, calculating building heights using angles of elevation, figuring out roof pitches, overhangs. That's all tangent.
Ah, like using a clinometer, opposite over adjacent.
Exactly. Also in the energy sector, for optimizing solar panel angles based on the sun's position.
Makes sense. Getting the tilt right.
Even in medicine, interpreting angles in scans like MRI or CT scans can involve trigonometric relationships, including tangent, to understand spatial orientations.
So it's pretty practical, despite the sequence A000209 looking a bit abstract.
The applications usually rely on the fundamental ratio or slope aspect, often in well-controlled angular ranges, not necessarily the behavior for large integer radians.
Okay, that makes sense. So let's bring it back to our main audience, number theory students. Why should they care about A000209, the nearest integer to tan? What's the number theoretic hook?
I think it's a fantastic example of the interplay between continuous functions like tangent and the discrete world of integers.
Okay.
The simple act of taking the nearest integer forces you to confront deep questions about how the values tan are distributed. How often does a specific integer appear in the sequence? How close does tan get to integers? Does the sequence have statistical patterns if you look at a modulo some number m?
Ah, so questions about distribution, frequency, modular properties.
Exactly. These are bread and butter questions in number theory. And here, they arise directly from the properties of a trigonometric function and its relationship with the irrational number pi. It connects analysis, geometry, and number theory. How do integer inputs behave inside transcendental functions? What patterns emerge or fail to emerge?
It's a doorway into Diophantine approximation territory, maybe. How well can rationals, or related values, approximate irrationals?
Precisely. It touches on those ideas. How well can multiples of pi 2 be approximated by integers effectively? That determines how large the values in the sequence can get.
So a sequence that looks simple leads straight to some quite profound number-theoretic questions. Okay, let's try to sum up our deep dive here.
Sounds good.
We looked at OEIS A000209, which is the sequence formed by taking the nearest integer to tan n, where n is in radians. While the definition is straightforward, the sequence itself is erratic, jumping between small integers, zeros, and occasionally very large values.
Like that negatives 226.
And the reason for this complexity lies fundamentally in the irrationality of pi. Because n radians never perfectly aligns with the zeros or asymptotes of tangent, and because n mod pi densely fills the interval 0 pi, tan n can approximate any real value.
Making its nearest integer jump around unpredictably. It's a beautiful illustration of how integers interact with continuous periodic functions tied to irrational numbers.
And it serves as a great starting point for asking deeper questions about value distribution and approximation core ideas in number theory.
Absolutely. Even simple-looking OEIS entries can hide deep mathematics.
Definitely food for thought. So, for a final thought to leave you with, we focused a lot on pi being irrational. But pi is also transcendental. It's not the root of any polynomial with integer coefficients. How might this deeper property, transcendence, influence the fine structure or the statistical distribution of A000209 or similar sequences involving trig functions in the very long run?
Ooh, that's a deep question. Does transcendence impose even stronger constraints on the distribution than just irrationality?
Something to ponder. We encourage you to explore A000009 further, maybe compute more terms, look for statistical biases, or just contemplate that fascinating connection between the discrete and the continuous. Thanks for joining us on this deep dive.